Greetings, chemistry students. Today we're going to jump right into the next part of our introductory unit, which is going to be on atoms and chemical nomenclature. So, the first thing is some stuff that you're probably already familiar with the structure of the atom. You've got protons, neutrons, and electrons. Protons have a positive one charge, neutrons have no charge, electrons have a negative one charge, which leads to the lamest joke in all of chemistry. A neutron walks into a bar. The bartender says, "For you, no charge." Protons and neutrons have a mass of 1. Electrons, their mass is so small we round down to 0. Protons and neutrons are in the nucleus, and electrons are in the electron cloud surrounding the nucleus. Electrons are where all of the really interesting chemistry happens, and what we'll spend a large portion of our time in this course discussing. That's just a brief overview. Um, we have atomic number is how many protons are in the nucleus, which is also the number of electrons because the charges need to be balanced out. And then the mass number would be protons plus neutrons. We'll focus on this in a lot more detail in just a little while. Not today, though. So, next, oxidation number. This would be the charge that an atom has when it gains or loses electrons to form compounds. And atoms generally want to have a filled outermost energy level, which typically works out to be 8 electrons. And so, to do so, they will either lose electrons, therefore becoming a cation or positive ion, because they have more protons than electrons, or they gain electrons and become an anion or a negative ion. And they do this in a fairly predictable way for a lot of elements on the periodic table. For instance, for elements that are in group 1 of the periodic table, they tend to lose 1 electron and have a positive 1 charge. Elements in group 2 become positive 2 charge. The noble gases over on the far right hand side, they don't do anything, they have no charge. The halogens, group 17, negative 1 charge, negative 2 charge, negative 3 charge. This group right here can be plus or minus 4. And the boron group is typically a positive 3 charge. So these oxidation numbers are fairly predictable for a large number of elements on the periodic table, but not all of them. So when you make an ionic compound, it's typically formed between metals on the left side of the periodic table and nonmetals on the right hand side of the periodic table, where the metal loses electrons, becoming that positively charged ion, and the nonmetals gain electrons, becoming that negative anion, and then they stick together to make an ionic compound. So these things form very predictable formulas when they make compounds. So to write an ionic formula, you write the symbols of the ions, putting the positive one or the metal first. You assign their oxidation numbers. Then you assign subscripts to make the charges equal. And then you get rid of any ones that you may have had. So let's go back to the periodic table. We've got this little dividing line here that, generally speaking, things on the left side of the periodic table are metals, and things to the right hand side of the line are non-metals. Right? So if we wanted to write the formula that's formed between, say, calcium and bromine, calcium over here has a positive 2 charge. Bromine over here has a negative 1 charge. So to make the charges equal, we need 2 negative 1s to go with our positive 2. So it's CaBr2. It's that simple. If we were doing something with, for instance, potassium and fluorine, well, potassium's a +1, fluorine's a -1, so it's just Kf. You don't need to put any subscripts there. And your final formula doesn't have the charges either, so you can erase the charges when you're done. If we were going to name these things, it's really simple to name. ionic compounds, you write the name of the first ion. Transition metals will add a little second step we have to do with Roman numerals. Then you write the name of the second ion and change the ending to IDE. So let's go back to these two examples. CaBr2 would be calcium bromide, and Kf would be potassium fluoride. You don't capitalize the names of compounds. They're not proper names, if you will. So now let's take a look at something that involves some transition metals. Transition metals really make things a little bit trickier. So that's typically speaking this region of the periodic table here, and also the guys hanging out down there at the bottom. Uh, what makes them interesting is they can have multiple oxidation states. So, for instance, titanium right here can have several different charges. So, titanium can form the compound TiO2. So, if we were to name this, well, that's titanium. And then we need to specify its charge because we don't know it. And then the O is oxygen, so that's oxide. Now, since oxygen over here always has a -2 charge, we know oxygen's charge is -2, and we have two oxygens. So if we have two -2s over on the right-hand side, then the titanium must be a +4 charge, and so we call this titanium 4 oxide. Similarly, if we had just TiO, we would call that titanium 2 oxide. So the Roman numeral represents the charge of the metal. Now, it gets even more complex than that, if you will. So let me cover the other cases. There are a couple of elements that, even though they're not transition metals, you need to specify the charge. That would be our friends tin and lead down here, because they can either have a +2 or a +4 charge, so you need to specify that with Roman numerals. And then there's a couple of elements that you don't need to specify their charge because it's always the same. For instance, silver is always a +1, zinc is always a +2, cadmium is also always a +2. So for instance, silver oxide is not ambiguous because silver always has a +1 charge. Oxygen's a -2, so it's Ag2O. We have to use Roman numerals whenever it's ambiguous because you could be referring to one of a variety of compounds. Every compound needs to have its own unique name. If you want to know who to blame for that, there's this organization called IUPAC, the International Union of Pure and Applied Chemists. Their functional headquarters are in Durham, North Carolina, and Research Triangle Park. They came up with all these rules for naming the compounds. One last thing to consider is polyatomic ions. And those are ions that are made up of more than one atom that function as a single group. And when you name compounds that have polyatomic ions, you don't change the endings. I'm putting a link to a list of polyatomic ions that you can refer to. You do not have to memorize them. Most of the polyatomic ions are anions. The only one that's positively charged that we deal with on a regular basis is ammonium, which is NH4+. So for instance, NH4 3N is ammonium nitride because nitrogen's a -3 charge and ammonium's a +1, so we needed 3 ammoniums. That's also why we use these parentheses around it. Let's look at a couple of other examples. We could have PbMnO4 4. That would be lead. And then permanganate has a -1 charge, and we have 4 of them. So lead must have a charge of +4. So it's lead 4 permanganate, which is one of those polyatomic ions. Or we could have something a little bit simpler than that. We could have Cu2CO3. That would be copper. Then we need to specify its charge because copper is a transition metal. And CO3 is carbonate. And carbonate has a -2 charge. So since our carbonate is -2 charged, our total copper charge must be +2. So each of our 2 coppers is a +1. So it's copper 1 carbonate. Hopefully, this is bringing back some memories from your previous chemistry classes and you're starting to refresh your brain on how this is done.